Hey, what's up, guys? So this is going to be the complete hardware walkthrough for the trigBoard project. This has been a very long-running project. Here you can see some previous revisions of the board. This is version 1, here's version 2, all using through-hole components. So everything you see here on this tiny little board here can be replicated on a breadboard using through-hole components. In case you're not familiar with the trigBoard, it's a simple IoT project. It's got an ESP8266 and a whole bunch of circuitry down here to allow it to sleep at less than 1 microamp, wake up from a digital input. It also wakes up once an hour on its own to check the battery voltage. And the whole point of this project is to send me a push notification on a digital input trigger. So that was the sort of the inspiration for the project. Of course, I've hooked it up to other things. Right now I have one of these boards on every door in my house. I also have a board out in the front yard, actually working as a weather station with a BME 280 on it. I've got one in the backyard monitoring the temperature of the water inside my hot tub, and that's using an LMT01. I also have a camera hooked up to one of them, so it sends pictures when the door opens. So there's a lot you can do with this board, and I'll talk about all of those projects in future videos. But the focus in this video is to work through that complex circuitry as to how it's able to wake from a digital input and still maintain that sub 1 microamp sleep current. So, settle in. This is going to be a long video, and let's jump over to the schematic. So, just before I jump into it, I want to first show you one approach you might be thinking. So, if you had one of these door sensors, these contacts are typically normally closed. So, right now I have the magnet right up to the sensor. So, this contact is closed. So if you were to monitor it with a standard style digital input interface, you would need a pull-up resistor, so when that contact opens, it pulls your input high, and then of course when the contact or the door is closed, you have a digital low. This is fine, but the problem is that this is a normally closed contact, so this is always closed, thus creating that path to ground through this pull-up resistor at all times. So with a 10k ohm resistor and a battery voltage of 4.2 volts, if that was your pull-up voltage, you're pulling 420 microamps. Even with 100k, it's 42 microamps, 1 meg, 4.2 microamps. I really don't like to get into the megs of ohms for a pull-up resistor, especially because then your input becomes more vulnerable to noise and blips, and if you had some cable length out here, you could falsely trigger or wake your processor up. So that's sort of the magic with the trigBoard circuit. I actually do not have a pull-up resistor, and that's how I'm able to establish sub 1 microamp type sleep currents. This is the schematic here, and I'm not sure if this is going to work, just showing you everything on a paper schematic or not. Before jumping into all of this, let me just explain at the highest level what's going on here. So we have a voltage regulator on the board, and this sets up the 3.3 volts for the system. This is what everything is ran off of. The ESP8266 gets its 3.3 volts from this regulator. This regulator has an enable pin. That enable pin is driven from a timer chip, the TPL5111. This wakes up once an hour, pulls on the enable pin high, wakes it up, and the ESP8266 wakes up. It has a way to check whether the chip was woken up from an external source or the 1 hour timer. And we'll get into that in a second. So what's cool about this timer chip is that it also has this delay input. And the delay input is how you set the sleep interval, or how often you want it to wake up. Right now I have that set for 1 hour using a 124k k ohm resistor pulled to ground off of the delay pin. But at any time, you can wake the timer chip up by pulling the delay pin to VBAT, okay, which is the battery voltage. So once I discovered that, well, we could actually potentially have that input be driven off of a digital input. And that's what all of this circuitry in here does. So that's very cool. And what I also wanted to do was, say you open the door up and leave the door open. I don't want any sleep current in there either. I want it to still be able to sleep at that sub 1 microamp level. So there's a little bit more complexity here in the design to allow for that. So working now backwards, we can see over here, this is the other JST. There's two JST connectors. One's for the battery, one is for this digital input. So on the digital input side, by the way, you can see on the schematic here, we've got all of the locations marked where I have a logic analyzer probe hooked up to. So on the digital input here, one side is VBAT and the other is the actual input in. So with the switch, when the switch is closed, this input here is high to VBAT. So let's go ahead and actually trigger this so that I've got the plots here to kind of walk through. So I'm going to go ahead and start a trigger, and then we're going to open the door, wake the board up, and we should in 5 seconds here get a notification, and sure enough we got that right on the phone. Okay, so we can go over here now and we'll talk about all of these channels, but oh, you know what, I gotta change something. One sec. Okay, trying that again. I had the wrong trigger set up. So now we have the right trigger, and you can see here the sensor is at channel 0, and when that goes low, I've got some digital plots here and analog just for reference. So you can see the digital is nice, clean. You can see when that goes low, then the output to the timer goes high after some period of time. So right here at the terminal block, we've got a probe, you can see falls low. The supervisor chip, and this is the secret sauce to the trigBoard, is that I'm using a low voltage supervisor chip so that when the input voltage falls low, this will actually drive its output hard low. Okay, so kind of a cool way to monitor a digital input. So right here we have that pin that goes low, the input to the supervisor, and then right over here, supervisor output, there's where it drives low. That's when it detects that that voltage went away. And interestingly, we've got a pretty long delay there of about 100 milliseconds between when it actually triggered versus when it detected it. And then from there now, immediately to the transistor, this is channel 2. And then down through this green line, we are enabling Q3 to allow VBAT to go into the timer chip. So it's mimicking what this wake button does here. So it's pulling Q3, which is a P-channel MOSFET, pulling its gate low. And I'm showing you this with a highlighted route here, and that's because I have circuitry on here to allow for the detection of a digital or a normally open style contact. So this right now is closed, and you want to trigger on a opening of this contact. A normally open style contact would be the other way, so it would trigger when this contact closes. So I've got some solder jumpers on there to allow for that, and I've got some information up on the wiki for this board, so if you want to experiment with that, but everything else is the same. This basically just inverts the output from the supervisor. Okay, the sort of clever part of this driver circuitry to Q3 is right in here. We've got a resistor and a capacitor in series. And the reason for that is because normally this output from the supervisor is high. And you can see that right here. We're sitting at about the battery voltage right there. So the voltage right there is high, and the voltage right over here to the gate of Q3 is high because it's pulled up with this 100k ohm resistor. So you have the same voltage across this capacitor. So when the supervisor pulls low, the capacitor discharges down through the supervisor. So you've got a little bit of time in there. Well, immediately the pin goes low through there because you've got this capacitor and both sides are at the same voltage potential. So immediately when you pull that low, you have that dead short through the capacitor, through the 100 ohm resistor, and that's for current limiting, down low, and then it starts charging back up slowly. And you can actually kind of see this. So to the transistor, right at this point here, you see we pulled the gate there low, Q3, and then it charges back up, all the way back up to the battery voltage. So that's how we're able to get a quick pulse there on Q3 to wake it up. Again, I don't want this to be leaking current when the door is left open, and that's exactly how this works. Because if I didn't have this resistor here, or this capacitor right through here, well, this would just sit here low, and I would have my leakage path right through this resistor down into the supervisor. Okay, I know I went a little crazy with the low power design here, but I wanted to really achieve that sub 1 microamp type sleep current. So, and that's how I'm able to do it. Okay, so right through here, now we're at the transistor. So Q3 is yanked low, and immediately the output right here is channel 3, and that's to the timer, and it wakes up. So we wake the timer up, and like I said before, then it can drive the voltage regulator high. So this is to the regulator, and you see now we have a signal there going high, and then sometime after that, we then have our 3.3 volt rail. So we kind of look around here, we can see at the point of the timer waking up to the time we actually get 3.3 volts is about 50 milliseconds. Okay, so now we're awake. Now we have our 3.3 volts. The ESP8266 is awake, and it's booting up, and the first thing it does is check this pin right here, external wake. So this is fed off of Q3. So when Q3 turns on, we have VBAT at the gate of Q4. This is an N-channel MOSFET, and this will pull low. So the external wake pin is low for a period of time until the capacitor is charged up, and then Q3 turns back off. So you can see here, as that capacitor charges up, bam, right there, the timer Q3 is then turned off, and then the external wake pin yanks back up high. So we really only have a brief amount of time during boot up here from that point to this point right here. So we have 1.24 seconds right here for the ESP8266 to boot up to check this external wake pin to see if it was an external wake or not. Again, a lot went into actually deciding all of this. I had to find the perfect set of values for this RC circuit, the pull-up resistor here, considering also the VGS values for Q3 and Q4, and the boot up time for the ESP8266. So that's why I'm at now Rev 4 of the design, but it works great. Okay, so at that point now, we've checked it, we know it was an external wake, and then we're sending out our push notification, and finally the ESP8266 kills itself with using the done pin. So it drives that done pin high, and then you see the regulator drops out, then the 3.3 volts, which takes out the external wake as well, because that's pulled high to 3.3 volts. And that's the whole thing. Oh man, that was a lot of talking right there. Okay, so The one other thing I want to quickly show you is to simulate a timer wake, which is when this wakes up on its own. And to do that, I'm just going to quickly tap the wake button here. So I'm going to go ahead, change my trigger here. I'm going to reset that. And now I'm going to wake on a rising edge of the timer. And let's go ahead and tap that. Start that, tap. And now you will see it'll wake up. It did wake up and went back to sleep immediately. So you see here now our timer here woke up. There was no sensor wake. There was nothing on the supervisor. There was nothing on the transistor. So you see the timer woke up right there. Then we gave it the regulator. The enable pin went high. Then the voltage came up. So you had the 3.3 volts. And you might be looking at the external wake pin, and you see how this is low, because when I do check that to be low, I would see that as an external wake. But the time from the 3.3 volts going up till the external wake goes back high is only 185 milliseconds. So I'm actually waking up somewhere over here, because when I do tap on the wake button right here, it is applying VBAT to the gate of Q4, and it does turn it on, and you can see that. So if I just look right here at the time I'm holding the timer, right there is the time that the external wake there is. Well, actually a better way of looking at it is right there. So you can see that the external wake there turned back off as soon as I let go of the button. Whew, okay. So there's kind of a lot going on here. Now, again, there's some corner cases and some other things going on in here that I haven't talked about. Like if you open and close the door very quickly. Maybe I can show you some things like that. Okay, so I had to play around with it a little bit, but this is something that I built into the design to actually protect it. So if you were to open and close the door, you know, we had that capacitor here, down here, actually charging up when you trigger it. So it's charging up. But what happens if you then quickly open and close the door? So when you close that door, now you have the voltage output from the supervisor right here at the other side of the capacitor. So you have the capacitor charged voltage plus the output voltage from the supervisor at the gate of Q3. So that's why I added in D2 right here to clamp it at VBAT. And without that, you would have double the battery voltage. So looking right here, you see right here is the initial trigger, and then I was kind of screwing around with it. It's charging up. And, you know, I'm kind of also, I have to catch it where the supervisor would drive hard high. So right here at this point is when I close the door back up, and you see the supervisor output shot back up to 3.7 volts. And then right here, the transistor, which is the gate of Q3, clamps. And that's where it actually clamped right at it. So that's to protect the gate there of Q3. And then it just stays there and everything is fine. So anyway, and it also turns off the timer because this now is clamped right there at Q3. Turns off the timer. The external wake also is turned off. So that's something, you know, if you're bouncing the door on it, you could actually trip out the ESP8266 to think that it was a timer wake. But again, that is if like you open and close it real quick, kind of like what I was doing with just tapping the wake button. Okay, well, anyway, hopefully that wasn't too boring. Let me show you a couple other things, though, real quick here. I focused mostly just on the wake circuitry, but over here we have the battery voltage monitoring circuitry. And this is a switched circuit because I want to monitor VBAT without having any leakage whatsoever. So I'm using a P channel and an N channel MOSFET here to allow for the battery voltage. And actually, I kind of changed this around a little bit. Originally, I had a digital pin enabling or disabling this. Now when the 3.3 volts comes up, it turns on Q5, and then Q5 pulls the gate of Q6, which is a P channel, low, and now you have VBAD going through this voltage divider right here into the ESP8266 analog input. Okay, so there's nothing too fancy about that. I also added battery voltage or battery charging over here. This is just using the popular MCP 73831, charging at 500 milliamps. Got the micro USB connector on there. Got your blue LED, the GPIO 0 and reset buttons are broken out so you can put it into programming mode. And then you have the ESP8266 with some spare I/O broken out to the side here for whatever sensors you want. There we go. Kind of. Okay, so anyway, hopefully that was an interesting video for you. We could get into this even further if you wanted, but I think this video has gone on long enough, at least for a part 1. So let me know if you want more of this. Otherwise, we'll move on and we'll start talking about the firmware to do all of the different things, including working with push-bullet, Slack, Adafruit IO, pushover, and a lot of other things. So that's it. Thanks for watching.